Hey everybody. So now we're really getting into it now because in order to understand how main sequence stars work, well how any star works, but specifically main sequence stars for now. Um, the structure of a main sequence star is a story of two forces, right? A star has a lot of mass and therefore strong gravity, right? So the gravity exerted by all that mass, right? Every atom in the star is pulling on every other atom, and they're all pulling themselves together, which causes, all of this mass to want to come toward the center, right? So gravity, every atom in the star is being pulled by gravity toward the center. So why doesn't the star collapse? Well, because there's an outward force pushing the gas out, and that is radiation pressure, right? So, in general, and there's more complicated steps to it, but in general, right, the star has two sections, right? The core is the center of the star. It's the only place where the star is hot enough for hydrogen fusion, right? 15 million Kelvin is the magic number, where once you've compressed this hydrogen to high densities and temperatures over 15 million Kelvin, then the two hydrogen atoms won't just collide and ricochet off each other, but they will actually stick together and fuse into helium. And that releases energy, right? And so in the core, the two hydrogens are fusing and then, doing the three-step reactions in the proton-proton chain series to produce helium and photons and neutrinos. In the envelope, you still got hydrogen. It's still hot, but not hot enough for fusion. So in the envelope here, you've got all these protons and also some helium, right? It's like 3/4 hydrogen, 1/4 helium, approximately, right? And these hydrogen atoms they're hot, they're moving fast, but they're just colliding off each other. And then the photons from the core come out and hit them. And when that photon hits the proton, it's going to push the proton outward, right? So all of this radiation trying to work its way out from the core, those photons keep running into other atoms. They keep bouncing off the atoms, bouncing and bouncing and bouncing and bouncing, trying to work their way out. And as those photons keep hitting the hydrogen atoms and the helium, those collisions of the photons hitting the atoms exerts this outward pressure. That is what we mean by radiation pressure, right? Radiation pressure is this outward pressure caused by heat, caused by photons, caused by light. The light that is trying to get from the core out to the photosphere, because once the light reaches the photosphere, then it can escape from the star and shine out into space. And that's the starlight and the sunlight that we see. But as long as the light hasn't escaped yet, as long as that light is just ricocheting over and over and over again, bouncing off of atom after atom after atom, all of those collisions just pushes on the pushes on the atoms, exerting this outward force, right? The light trying to work its way out and running into protons and helium and atomic nuclei along the way. And a main sequence star, a star is nice and stable and well behaved as long as those two forces are in equilibrium, right? The gravity pulling in, the radiation pressure pushing out, and as long as every location in the sun is in balance, right? The star doesn't collapse or expand. That is what we mean by this hydrostatic equilibrium, right? Usually you think hydro as in water. Well, the sun's not water, but it is a fluid. It's a gas, right? It's a gas that can expand, contract, it can move around. So hydrostatic, meaning that the fluid is static. The fluid is not expanding or contracting, right? The fluid is not moving around. The fluid is static. It is stationary. It's in balance. That's what we mean by equilibrium. right? It's the equilibrium, the balance between radiation pressure pushing out, gravity pulling in, and as long as those two forces are in balance, then all of the gas stays where it is. But that equilibrium is only able to be maintained as long as there's more radiation coming out of the core, right? As long as there's nuclear reactions happening in the core, those nuclear reactions produce photons. Those photons collide with atoms, exerting that radiation pressure, until eventually the light works its way out to the photosphere, escapes, and once the photon shoots away, it can't exert any pressure anymore. Which means more photons have to come out of the sun to replace the photons leaving. Right? In order to maintain this balance, new light has to be produced, new energy, new heat, new radiation pressure has to be produced to replace the radiation that escaped from the star in the form of the star's luminosity. But how many nuclear reactions will happen in the core in a second is a little bit random, right? Exactly how many reactions will happen. You could have a few more, you could have a few less, but what happens? Well, let's say, by sheer happenstance, right, a little more energy is produced in the core, right? And that, if there's more energy produced in the core, then that radiation pressure is going to be stronger, and therefore the radiation pressure is greater than gravity, and that's going to push the star outward, right? The star is going to expand because the outward pressure is stronger than the inward pull of gravity, right? So, if the star expands, then its density will decrease. And if the star expands, then its density in the core decreases, the pressure and the temperature in the core decreases, and if the temperature and the pressure in the core decreases, then there will be fewer nuclear reactions per second. If there's fewer nuclear reactions per second, then that means what happens to the energy generated? That will also go down. So then, if there's no more extra radiation pressure, then the radiation pressure will decrease, the gravity is now stronger than the pressure, and that gas will recompress on itself. So what just happened, right? By sheer happenstance, there's too many, or not too many, but there's extra nuclear reactions happening, and that creates some extra heat, some extra radiation pressure, and the star expands. But by expanding, the star cools off. That throttles back on the nuclear reaction rate, which means there's less energy generated. The problem in the beginning was there's too much energy generated. So the star expands a little bit, cools off a little bit. That decreases the nuclear reaction rate, decreases the amount of energy until the radiation pressure and the gravity come back into balance. That gas that expanded recollapses and it shrinks back to its original size again. Or, by sheer happenstance, fewer nuclear reactions happen in a second. And so if fewer nuclear reactions happen, then there's less radiation pressure, gravity becomes stronger than the outward pressure, and the star shrinks a little bit. But if the star shrinks a little bit, then the temperature's going to go up, right? What happens to a gas when you compress it? It heats up. If the gas heats up, then you're going to have more nuclear reactions per second. You're going to increase the amount of energy that gets created, and you're going to get more radiation pressure. That increase in radiation pressure causes the gas to re-expand until it goes back to the size it was before, and the pressure and the gravity come back into balance. Basically, a main sequence star is so stable and well-behaved and long-lived because it has this thermostat, right? If the star makes too much energy, then it expands, cools off, and brings the energy back into balance. If the star doesn't make enough energy, then it shrinks a little bit, heats it up, makes more energy, and brings the pressure and gravity back into balance, right? Either it has like a thermostat, right? If the star heats up too much, it expands and cools off. If the star cools down too much, it contracts and heats back up. So that a main sequence star is stable. And if it heats up or cools down, then it will compensate to come back into balance, into equilibrium, and everything goes back to the way it was before. It allows for a little bit of randomness, a little bit of the randomness of exactly how many nuclear reactions are going to happen in a second. If that varies by a little bit, it's okay. The star will adjust, expand or contract, heat up or cool down to bring the pressure and gravity back into equilibrium. This is how main sequence stars live so long. This is how main sequence stars... This is why stars are main sequence stars for 90% of their lifetimes, is because as long as the star can maintain this equilibrium, as long as the star can maintain this thermostat of keeping pressure and gravity in balance, everything stays fine. And the star just keeps on living, keeps on humming along. As long as there's hydrogen in the core to burn, right? Because the one thing that has to happen is you need to keep on having nuclear reactions so that those nuclear reactions can generate new radiation pressure to keep gravity in check, right? And so a main sequence star, every main sequence star, the low mass ones, the high mass ones, the ones in the middle, every main sequence star is defined by having pressure and gravity in hydrostatic equilibrium powered by the fusion of hydrogen into helium in the core. As long as there's hydrogen fuel in the core to burn, the star can maintain the balance and stay a main sequence star. It's when the star runs out of hydrogen that it can't maintain the balance, and then the star evolves off the main sequence and becomes the other types of stars. A red giant, a supergiant, a white dwarf. And that's a story for another day. But as long as the star can maintain that structure, as long as the star can stay in balance, it'll just stay like it is with a constant luminosity, constant temperature, constant radius as a main sequence star, as long as it's got hydrogen fuel to keep going. So, in the space below, draw a diagram for the two parts of the star, labeling each with its name. So you've got the outer envelope here, and the core in here, right? Where does the fusion take place, right? Here's the fusion of hydrogen into helium, right? Hydrogen getting consumed and turned into helium in the core. What's the approximate temperature? Well, the core is over 15 million Kelvin. And the envelope is, well, the envelope right above the core is only a little bit cooler than the core, right? The envelope right above the core is a little less than 15 million Kelvin. And then as you go from the core out to the surface, from the core out to the photosphere, then the temperature drops, where it's 15 million in the core, and it cools off to a chilly 5,800 Kelvin on the photosphere. Because that's where the light escapes from, right? The last gas that star scatters off of before it escapes, that's the gas that determines the spectrum that we see, right? The light that we see from the sun is not made by the surface. It's made in the core, and it just escapes from the surface. So when you look at the spectrum of the sun, the the sun's blackbody spectrum, the sun's continuous spectrum, tells us that it has a surface temperature of 5,800 Kelvin. Right? We know that from the peak wavelength of the spectrum. That's just the surface, right? The spectrum of the sun doesn't tell us what the temperature in the core is. That's where you can't see down into the core, right? The inside of the sun is opaque, right? We can't see in under the photosphere. So how do we know how hot this is? Well, a couple of ways. One is by doing the math to say, okay, if the sun is 5,800 Kelvin here, how hot must it be once you get down here? How hot must it be once you get down here? How hot must it be once you get down here? Et cetera, et cetera, et cetera. So you can do the math and let the physics tell you what the temperature must be at every layer inside the sun. The other way that we know what the temperature is from the neutrinos, because the gas takes up to 1 million years to keep bouncing around inside the sun over and over and over and over again before it finally reaches the photosphere. But the neutrinos made by the hydrogen fusion reactions in the core, those neutrinos leave immediately. They can fly right out of the sun for us to detect here on Earth. And so they're very hard. It's very hard to see a neutrino. But now that we've built detectors that are sensitive enough to find these things, the number and the energy of the neutrinos that we do see tells us that the temperature inside the core must be about 15 million Kelvin, just like the math tells us it should be. Draw arrows to indicate where the squeezing is taking place. That's forced the hydrogen to fuse. Well, the squeezing is, gravity, right? The weight of all this gas from the envelope pushing down on the core is what drives the core to be hotter, higher pressure, hot enough for fusion. All right. Suppose a star produces too much energy in the core. Describe what happens to return the star back to balance. Okay, so you could write this out any number of ways. You could write it out in sentences and paragraphs if you wanted to. I'm going to use a little bit of shorthand here, right? So I'm going to call the radiation pressure P for pressure, and I'll call the gravity G, right? So you got too much pressure. You got too much radiation pressure, right? The star made too much energy, and that's going to give you too much pressure. So what happens? So the star expands, right? If pressure is stronger than gravity, then the pressure pushing out is stronger than the gravity pulling in, and that gas will get pushed outward. So it expands. Which means that now the gas, if the gas takes up more space, there's less density, right? So the density and the temperature drop. And if the temperature drops, that means the nuclear reactions. I'm going to write reaction RXN, just like you probably saw in last time you had a chemistry class, right? So the nuclear reaction rate goes down, right? Because in order for the hydrogen to fuse, it's got to be hot enough. If the temperature drops, then the nuclear reactions won't stop. The core is still over 10 million Kelvin, but it'll slow down. If the nuclear reaction rate slows down, then the pressure drops, and it comes back, and then pressure and gravity come back in balance, right? This problem started with too much pressure, which means the gas expands, cools off, the nuclear reactions slow down, and that reduces the pressure back in balance. If there's not enough energy being made in the core, then the opposite happens, right? If there's not enough energy, then the pressure drops. Pressure is weaker than gravity, which means it will collapse a little bit. The star will contract. You could say collapse or contract to get smaller. Same way of saying the same thing, right? If the star collapses down a little bit, that's going to cause the density and the temperature, what happens to a gas when you compress it? It heats up. So the temperature is going to get hotter. If the temperature inside gets hotter, then the reaction rate increases, right? More nuclear reactions happen in a second. If there's more nuclear reactions happening in a second, that extra radiation trying to work its way out increases the radiation pressure, and the pressure comes into balance with gravity, right? If there's not enough pressure, the star shrinks, heats up until the pressure brings gravity back into balance. That's how you maintain this equilibrium, right? What is hydrostatic equilibrium? Hydrostatic equilibrium is where the radiation pressure everywhere in the star balances out the gravitational pull inward, right? Notice that in both of these explanations, the gravity's not changing, right? Because gravity is caused by mass. The mass of the star isn't changing. Gravity is this constant threat trying to make a star collapse in on itself. And the only thing able to fight against gravity is the outward push of all those photons made in the core trying to work their way out. The pressure and the temperature and the nuclear reaction rate can adjust, increase or decrease, because in order to survive, this star has to keep that gravity in balance. And as long as it's in balance, then the hydrostatic equilibrium is maintained, and the star lives for another day. All right. I hope that makes a bit of sense. Post your questions if you've got them. But if that's making a decent bit of sense, then you're ready to move on to the next thing about how main sequence stars like the Sun survive, and then the really interesting story of what happens when you break the hydrostatic equilibrium. What happens when pressure and gravity get thrown out of balance? Because that's when the star starts evolving and ultimately dying, and that's when things get even more interesting. So, as I said, a story for another day. We'll get there shortly. All right. Have a good day, everybody.